Well, this is a theorem that will enable us to change our variables to polar form in case the integrand might be worth doing that, and it might make things much more convenient if I were to do that. I hope you understand that. Do you understand that?
Okay. Okay. Okay, bye.
Well, see ya. Sorry you have to leave, but that's the breaks, I guess. So if we have our R with an outer boundary G2 of theta and an inner boundary G1 of theta, and both are greater than or equal to 0, so that is an issue that might come up, and I would recommend whenever you can to use symmetry when you calculate these double integrals in polar coordinates, because if the R value is negative, you'll be subtracting some area that you don't mean to. So if this is true though, and your theta is a number between alpha and beta, where of course beta minus alpha is less than 2 pi, can't do more than one revolution, and the upper limit, or the outer, the inner and the outer are continuous functions on the interval alpha to beta, and f, the function we're integrating, this one, is continuous in on our region R, then the double integral over the region R of f of x, y, dA could be thought of as the double integral, again, region R. But now this R, you might need to define it with polar limits, but will be f of R cosine theta, R sine theta, times r d theta. This part here is the dA. This is the function of x and y, with x and y replaced with r cosine theta and r sine theta respectively. So here's a problem. Find the volume of the region bounded by the following in sketch. So we got a couple things here. Z equals x squared plus y squared plus 1. You should recognize that as a paraboloid with circular cross sections parallel to the xy plane. Z equals 0, you should recognize, oh, that's the xy plane. And x squared plus y squared equals 4. Now that's true for all z, so that makes it a cylinder. So I can show you this function and rotate it about, etc. But now what I can't show you is, if I was looking down on it, maybe we get an idea. There's a circle of radius 2 that would be running around this thing, and it would be, the region would be above that circle in the xy plane and below this paraboloid whose cross sections are circles. So this picture doesn't quite do it exactly the right justice, because you can't see what we're trying to find is the volume underneath this and above that xy plane, z equals 0. So let's do that. I have a better picture of it here. It's kind of like, but I can't rotate this one. It's kind of like, it looks like a cylinder, except it has this, where the mesh is, it's like pushed in the middle, right? So I hope this picture makes it a little more clear what we're actually finding. So here's how you do it. We can start with this integral. Okay, that's just our function of x and y. I put dy first and dx second, and dy, since our region R is this circle in the xy plane, where, you know, actually circle of radius 2 in the xy plane, so therefore y would vary from positive square root of 4 minus x squared and to negative square root of 4 minus x squared, like the upper semicircle and the lower semicircle. And our y then would be, and again you can see this, maybe I can make it a little more visible if you're looking down on this, that our y values are going to go from -2 to 2. And so, if you can imagine this circle, maybe that circle, this circle here might show a little bit better. this is the integral that would give us the volume of this piece here with a pushed in center. Now, problems come up. Because number one, when I integrate this with respect to y, I'm going to get an x squared y here and a y cubed over 3 here. But look at these awful limits of integration I'm going to have to plug in. And then I'm going to have to integrate that with respect to x. And I just don't relish doing a problem that's that ugly. So, this may guide me when I set up this whole thing in polar coordinates. Having this picture, remember this is the picture of the region R that's the bottom of this solid whose volume I'm trying to calculate. So instead of the above integral, a simpler one is, well, R is going from 0 to 2. I could say, all right, let's see, RD theta, R goes from 0 to 2. Well, okay, pick any angle, R goes from 0 to 2. The inside goes to 0, the outside R equals 2. That's the circle, R equals 2. So that certainly made that part simpler. And then that square root of x squared plus y squared plus 1. Well, keep in mind, x squared plus y squared equals r squared. So it's just r squared plus 1. The RD theta, now I've got to tell you about the theta here. Now for the theta here, if I started drawing rays, I'd start drawing at 0 and quit when I get back all the way around to 2 pi. Now I'll be honest, you could probably use symmetry on this one and just go from 0 to pi and double it, or you probably could even go from 0 to 2 pi and multiply it by 4. I'm basing that on the symmetry of this region, right? The symmetry of this region. If I find 1/4 of its volume, then I could multiply by 4 and get its entire volume. If you want, at the end of me working this in the normal way, I'll come back and check that. Now, this is easy enough to integrate, r cubed plus r. Think about how hard this one was going to be after I integrated with respect to y. Ooh, you know, it gives me nightmares just thinking about it. So, but this one's piece of cake. R to the 4th over 4, r squared over 2. There, that part is. And r goes from 0 to 2. That's also nice too. So 16 over 4 plus 4 over 2. So 16 fourths, that's 4, plus 4 over 2 is 2. 4 plus 2 is 6. So it's 6 d theta, which integrating 6 d theta is too easy. It's just 6 theta, theta going from 0 to 2 pi, so we get 12 pi. And just to show you that if I would have used symmetry on this, I think I told you I could have gone here from 0 to pi over 2. And I hope you believe me on that, but just in case you don't, I wouldn't blame you for not believing me. But what I need to do in order to make this a little more believable, I'll have to say 4 times and then I'll paste that back in there. That's better. Okay, now this should also be 12 pi. And I'm just going to let the software evaluate that because, you know, you should see that and it shouldn't give you too much difficulty. But I did it once, that was enough.